Hi everybody. We had just started the periodicity chapter, and we are going to look at several periodic trends. We had said that an electron has two forces acting on it. A force of attraction to the nucleus, that's your nuclear charge. So the electron is attracted to the protons in the nucleus. But also we have a repulsion force of the other electrons acting on it. And so we had said that effective nuclear charge, or Z effective, is basically the actual nuclear charge, so the number of protons or the attraction to the nucleus because of the positive attraction, minus the repulsive forces, which is basically what we called shielding. So now we're going to look at each of the properties and their trends, both across a period on the periodic table and then down a group on the periodic table. So we're going to start with effective nuclear charge. So the first thing you want to do is define your property. So effective nuclear charge, which is basically Zeff, that is the reduced or net nuclear attraction due to the shielding of electrons. If you remember from last year, as you go across a period, Zeff increases. Let's say Zeff increases. And now we need to explain why. So like I said, the first thing is define your property, then say your trend. So across the period, Zeff increases. And then your supporting statements. Your supporting statements should be 2 to 4 statements. So in this case, we want to say why Zeff increases. And so Zeff increases because the nuclear attraction increases due to the addition of protons. The number of protons increases, so your nuclear charge increases, so the attraction increases, basically, that's what we're saying. And at the same time, shielding is minimal because the electrons are added to the same energy level. And so therefore, the net attraction, which is basically Zeff, to the nucleus is stronger or increases. So I defined my property. I said my trend across a period. I have a couple of supporting statements for why. And then I basically restated my trend. And you can restate it in other words, or you can restate it in the same words. You can just say, so Zeff increases. But it's nicer to kind of explain it again. Basically, the net attraction is Zeff. Let's now look at Zeff down a group or down a family on the periodic table. So as you go down a group on the periodic table, Zeff decreases, or the effective nuclear charge decreases. So that's my trend. Now I'm going to use my supporting statements. So you would say that's because shielding increases. Remember, that's the repulsion between the electrons. So the shielding increases because the electrons are now added to new energy levels. So therefore, the electrons are farther away from the nucleus. and so therefore your net attraction to the nucleus, which is basically Zeff, is weaker or decreases. So again, you go full circle. You define your property, then you state your trend, you have supporting statements. Your supporting statements usually have to do with shielding, and also your nuclear charge or your attraction. And so because the electrons are farther away, the net attraction is weaker. The next property we're going to look at is atomic radius. So again, first thing you want to do is define your property. So atomic radius is half the distance between two nuclei. As you define your property, you also say what units it's measured in. So in this case, atomic radius is a distance, so we use distance units, but these are very, very small distances, and so this is usually measured in picometers or nanometers or angstroms. Now on the test, you don't have to tell me, picometers or nanometers or angstroms. You can just pick one of them, and that's fine. Pico is 10 to the negative 12, nano is 10 to the negative 9th, angstrom is 10 to the negative 10, so either one is okay. So let's look at the trend across a period. If you remember from last year, the one-armed snowman, so if you look at the arm of the snowman, it kind of gets smaller and smaller. That was the size trend. And so across a period, your atomic radius decreases. So that's our trend. Now let's look at our supporting statements. So the atomic radius decreases because Zeff, which is the net nuclear attraction, increases. Zeff increases because the nuclear attraction increases due to additional protons. Your shielding is minimal because those electrons are being added to the same energy level. And so therefore your net attraction to the nucleus increases, and so therefore the electrons are pulled closer to the nucleus, so atomic radius decreases. So a lot of these, your supporting statements are basically the same because it's all about basically Zeff. That causes all of the different trends. So again, define your property, say what units it's measured in, say the trend, list your supporting statements, and then basically come full circle and restate your trend. Let's look at atomic radius as you go down a group. So if you remember again, the one-armed snowman, as you go down, it gets bigger and bigger. Again, that's your size trend. Let's draw it here. So it looks like this. It's your size trend. So as you go down a group, you can see that it increases. So let's come up with our supporting statements. Again, they should be basically the same as the ones we talked about for Zeff. So you would say that the atomic radius increases because Zeff decreases. That's because shielding increases because electrons are added to new energy levels. And so, therefore, your net attraction to the nucleus decreases. So therefore, there is less pull on the electrons by the nucleus, and so therefore your radius increases. Again, full circle. Alright, so usually most of the questions that you'll see, you're comparing between just two elements, either in the same group or the same period, so they're pretty easy to figure out which one is larger in radius. But what if you're given a whole bunch of different elements like this? So in that case, what you want to do is look at your periodic table and find all the elements that you're interested in. Look at them or circle them or whatever, and compare between them. So I think the best strategy to do this is to think of the trends again. And so as you go across, your size decreases, it gets smaller. As you go down, your size increases. So find the corner in the periodic table that has the smallest radii and the corner that has the largest radii. So since it increases you go down and decreases you go across, then this corner of the periodic table has the largest sizes or radii. This corner of the periodic table has the smallest radii. Okay, so if you're going from, or if you're using decreasing order, be careful because sometimes the question will ask you for decreasing or increasing. So decreasing means it's getting smaller. So you're going to start with the largest and go to the smallest. So you're going to start with this corner of the periodic table and go this way until you reach the smallest. Okay, now you're going to notice that some of them are in different groups and some of them are in different periods. And so, depending on what property it is, you kind of have to be a little bit careful because we're talking about size here. So, what do you think? The period or the group would be more important? I would say that the period would be more important, or the energy level would be more important. For example, the second energy level would be much smaller than the first energy level. So there's your first energy level, second, and third. So substances that are in the first, or elements that are in the first energy level, are all smaller than the second energy level, are all smaller than the third energy level when it comes to radius. And so when you look at these, you can see that potassium is in the fourth energy level, so that should be the largest. Then you have sodium, aluminum, and chlorine are in the third energy level, so those would be kind of in the middle. And then you have boron, carbon, and fluorine are the smallest, so those would be at the end. And so let's start ranking. So we said potassium is in the fourth, so that would be the largest, so that goes first. So we're going to start with potassium. Okay, then between sodium, aluminum, and chlorine, remember size decreases as you go across. So out of those three, sodium would be the largest, followed by aluminum, followed by chlorine. All right, then in your second energy level, again size decreases as you go across. So then the largest out of those three would be boron, then carbon, and then fluorine. Okay, next let's look at the radius of ions as opposed to radius of neutral atoms. And so the definition for ionic radius would be basically half the distance between not just any two nuclei, but two nuclei of ions, or 2 ionic nuclei. Either one's fine. So the units for this would be the same as atomic radius, so it would be measured in nanometers or picometers or angstroms, whatever you prefer. So we have 2 different kinds of ions. Remember, positive ions are called cations, and negative ions are called anions. Remember, cats have paws, so cations are positive. So here we're not really comparing between different elements. We're more comparing between an element, a neutral atom, and its ion. So a cation becomes a cation because it loses electrons. And so if you look at the electron cloud, it gets smaller. So a cation is always smaller than its parent atom. So let's explain that. So loss of electrons means increase in Zeff, or effective nuclear charge. Your shielding would decrease because you have less electrons to repel each other. And your proton to electron ratio increases. You have the same number of protons, but now you have less electrons, so you have more positives to pull in those electrons, and so therefore, should be 3. That's not that many. And so therefore, stronger nuclear attraction or stronger Zeff, we're basically restating this. And so therefore, electrons are pulled in, and so your radius decreases. All right, now let's look at anions. So anions, you're gaining electrons to become an anion. And so an anion is always larger than its parent neutral atom. Okay, let's look at why. So to become an anion, you gain electrons. So gaining electrons means that you have a decrease in Zeff. That is because your shielding increases. It increases because now you have more electrons to repel each other. Your proton to electron ratio decreases because now you have more electrons, so you don't have as many pluses compared to the electrons to pull them in, and so you have weaker nuclear attraction. So basically we just gave 2 statements to support that Zeff decreases. And so if you have weaker nuclear attraction, that means the electrons are held looser, and so therefore your radius is larger. Okay, so for example, let's say that you have sodium versus its ion, Na+. So if you want to compare the size of these 2, sodium, let's say is the size, Na+ would be smaller because it lost the electrons, and so your Zeff increases and so it pulls those electrons towards it more. If we compare, let's say, chlorine with its ion, so Cl-, Cl minus gained electrons, so your Zeff decreases, and so an anion would be larger than its neutral parent. So if you are looking at ionic size across the periodic table, and again we're comparing them to their parent neutral atoms. If you look at, across a group, so let's look at, sorry, not across a group, across a period. So if we look at the third period or the third energy level, for example, we have sodium ion, then magnesium ion, and then Al3 plus. Let's skip the fourth group here, or group 14. Then you have N3 minus, O2 minus, and F minus. So as you go this way, you're losing more and more electrons, so your size decreases. As you go this way, your size decreases as well. Here, you either gain 4 or you lose 4, and so you have a dramatic jump, basically. And so this would look like that. On your periodic table. So this would be the plus 4, this would be basically the minus 4, this would be the largest jump, basically, and this would be the smallest. Compared again to their neutral atoms, not necessarily to their neighboring elements. Next property we're going to look at is ionization energy. So ionization energy is the energy required to remove the outer electron from a gaseous element. Okay. Now, gaseous element, just because in order to ionize it, to remove an electron, it needs to be in the gaseous phase, basically. So this is the energy required. You have to put in energy in order to remove electrons. And so you have to put in energy because it's attracted to the nucleus. So you have to be able to remove it from that attraction. It is energy, so it's measured in joules or kilojoules and typically per mole. So measured in joules per mole, or typically actually kilojoules per mole. Because remember, a joule is very small. If you think about it again, you have to put in energy in order to remove the electron from the attraction, and it's attracted to the nucleus. And so that would mean that if you have high Zeff, high attraction to the nucleus, that means you have to put in more energy to remove the electron. So there's high ionization energy. If you have low Zeff, then that means you have low ionization energy, because if it's not attracted as much, then it's easier to remove. So let's look at the trend across a period. So across a period, Zeff increases, and therefore ionization energy increases. So let's look at our supporting statements. So we would say ionization energy increases because Zeff increases. That is because shielding is minimal, and that's because your electrons are added to the same energy level. I'm going to use N for energy level. And so your attraction to the nucleus becomes stronger. And so it is more difficult to remove an electron, and so it takes more energy to remove the electron. By definition, ionization energy is how much energy it needs to remove the electron. Down a group or a family, ionization energy. Well, let's think about this. Ionization energy is related to Zeff. So down a group, Zeff decreases, and so your ionization energy decreases. So let's look at our supporting statements. Zeff decreases. That's because shielding increases because your electrons are added to new energy levels. And so your attraction to the nucleus is weaker. And so because the attraction is weaker, that means it's easier to remove the electron, and so it takes less energy to remove the electron. So if you remember from last year, I always told you guys, think about the reasons first. Think through it. It's usually has to do with Zeff. So think about what your property means, and think about Zeff and how it relates to Zeff. And from your supporting statements, you should be able to come up with what the trend is. We just said that the ionization energy is a measure of the effective nuclear charge, or it's related to Zeff. So the higher Zeff, the higher the ionization energy. And so if you look at this right here, here's your nucleus with the positive charge. Here are your different electrons. And so here you would have high Zeff, and so high ionization energy. So the electrons here would be the hardest to remove. If you look at the fourth energy level, relatively speaking, compared to the first energy level, these would have low Zeff, and so low ionization energy. So these would be the easiest to remove. Okay, so the farther away the electron, the less energy required to remove it. So the lower the ionization energy. All right. Just so you know, we have several ionization energies. So ionization energy is the energy to remove the outermost electron. So we have the first ionization energy, we have a second ionization energy, we have a third ionization energy, we can have a fourth. And so the first would be how much energy you need to remove the first outermost electron. Second ionization energy would be the energy needed to remove the second outermost electron, and so on and so forth. So let's look at this graph right here. So this is the ionization energy. This is in electron volts. So it could be measured in electron volts or kilojoules per mole. It doesn't really matter. And so on the x-axis, these are actually the atomic numbers here. And so it shows the different atoms and their trends. And, take a look at all of them here. That should make sense for the most part, because we said that as you go across the periodic table, your ionization energy increases. So it makes sense, for example, that you go, from one element to the other, across a period, going this way or this way, those are all in the same period here or here. It increases, so that makes sense. And as you go down, it decreases, so that also makes sense. However, there are a few anomalies here. There are a few that don't really make sense. For example, let's compare between beryllium and boron. Beryllium is right after lithium. It's right here. And then there's boron. So this is boron. This is beryllium. So as you go from lithium to beryllium to boron to carbon to nitrogen to oxygen, it increases. So the general trend makes sense, but right here it doesn't make sense. We would expect that boron would have a higher ionization energy than beryllium. And so we want to explain that anomaly. Why is that? That's kind of an exception. And that is something that you would be responsible for on the AP test. So if you're given something like that, what I would do is I would start with your electron configuration. So beryllium is 1s2, 2s2. You can start with your electron configuration, or you can do an Aufbau diagram. It doesn't really matter. So it would look like this. There's your 1s, there's your 2s. Boron is 1s2, 2s2, 2p1. So there's your 1s, there's your 2s, there's your 2p, has 1 there. Now, what does ionization energy mean? Ionization energy is the energy required to remove the outermost electron. And so it's how much energy you need to remove this electron or this electron. And so what we notice is that beryllium has higher ionization energy according to that table there, or according to that graph. So we need to explain that. Let's look at beryllium here. The 1s and the 2s in beryllium and neutral beryllium are spin paired. So there's basically the orbitals are full. That makes it stable. If your sublevel is full or spin paired, then that makes it stable. If your whole sublevel. If you remember from last year, if the whole sublevel is filled or half filled exactly, then that's pretty stable. And so it's already spin paired. So if you remove that, then you don't have a spin paired anymore, and so that is not as stable. So let's write that down. The electrons in beryllium in 2s are spin paired, which is already a stable configuration. So therefore, it is more difficult to remove an electron. It takes more energy to remove the electron, and so you have higher ionization energy compared to boron, which has 1 electron in the 2p. If you remove that 1 electron in the 2p, you get a spin paired 2s, and so that is a stable configuration. So I would actually not just say this, but I would also add compared to boron. If you remove the 2p electron, then that becomes spin paired, which is a stable configuration. So you need to be aware of these anomalies. So it's as you go from the second group jumping to the 13th group, from the beryllium group to the boron group, that happens in all of the elements there. Okay, now let's look at another anomaly. Remember we said that as you go across a period, your ionization energy increases. So we saw one anomaly from boron, beryllium to boron here. We see another one here from nitrogen to oxygen. There's your oxygen right here. And so why is that? We would expect the oxygen to have a higher ionization energy. So let's look at their electron configurations here. So nitrogen, or let's look at their Aufbau diagram, that's even better. So you have your 1s that's filled, your 2s is filled, your 2p, you have 3 electrons, 1 in each of the orbitals. That's exactly half filled, so that is a pretty stable configuration. Now let's look at oxygen. 1s is filled, 2s is filled, your 2p, you have 4 electrons. Okay, ionization energy, remember, is the energy to remove the outermost electron. So in nitrogen, we would remove this electron. We'd go from them having 3 unpaired electrons, so it's half filled, to having a random number, it's 2. Compared to oxygen, if you remove this electron, then you have a half-filled sublevel, which is actually a stable configuration. So it is easier to remove this electron. That is more favorable than it is to remove this electron. So let's write that down. So we'd say nitrogen has 3 unpaired electrons in the 2p, which is a stable configuration. Therefore, it is more difficult to remove an electron, therefore higher ionization energy. At the same time, I would say oxygen has 4 electrons in the 2p. Removing an electron results in 3 unpaired electrons, which is a stable configuration. So therefore, easier to remove the electron, so therefore less ionization energy. Alright, that's it for the notes. Next time we're going to talk about photoelectron spectra, which is actually related to ionization energy. So have a great day, everyone.